I'm Justin.
I'm Ben.
And so today we're actually going to walk you through our hydrogen vehicle revitalization project. And I think straight up from the beginning, we're just going to show you what the vehicle is. It's that thing that's been sitting in the highway, maybe taunting some people who are walking past. Us having our 4 years through the pandemic, having seen a car that's kind of just sitting there, looking like a trike. And if you don't know what a hydrogen fuel cell vehicle actually is, it is this thing that I'm sitting on, bench style right now. It's also this thing that we had sitting in the service elevator at one point. Maybe you saw it running around the second floor of Singer. It might also be what our lovely driver, Hano, drove around in an engineering gala terrorizing the first floor of Singer Hall. Also the same thing we were working on literally 5 days ago, because there were things that we needed to install on it. And we're not going to actually get too deep into what a hydrogen fuel cell vehicle is and the theory of how hydrogen fuel cell vehicle works. But just for everyone to know, it's essentially harnessing the chemical energy of hydrogen and turning it into electrical energy to run an electrical motor. So it's a little bit different from battery EVs. And we're going to show you how it actually runs. Big portion of the first part of the project was getting it to run auto, blasting through our yellow cones, going about 12 to 25 miles per hour, depending on our conditions and depending on how warm the actual vehicle is. But now that you've seen the vehicle, let's give you a little context of like where we're coming from and why we started working on this project. And a good first place to start is to talk about the Shell Eco Marathon. Shell Eco Marathon is a worldwide engineering competition working on motorized vehicles, similar to Formula One actually, where we're working on engineering a really amazing vehicle to go on a track. But instead of going really fast on a track, actually we're actually build a vehicle that's the most fuel efficient, get the most mileage. And so a lot of different powertrain systems you can work on with Shell Eco Marathon, ranging from internal combustion engine hybrids, where you're looking to minimize the amount of unleaded gasoline you're going to be using in any single run, to battery EVs, which is minimizing the amount of kilowatt hours you're going to be using from your battery, then to our powertrain system, which is the hydrogen fuel cell vehicle, minimizing the amount of kilograms of hydrogen used in any single trial run. And what's really cool about the Shell Eco Marathon is that there are lots of categories of vehicles that we might be able to work on, ranging from the prototype vehicle from the very top you're seeing, pretty much looking like a airfoil at this point. Not a lot of constraints in terms of usability commercial-wise, versus the urban type vehicle where you're given a lot more constraints to build a vehicle that might be used in the next 4 or 5 years in the future. And that's all great. Shell Eco Marathon, worldwide engineering competition. Why did we decide to actually work on this as an E90? And the biggest first thing we noticed was this idea of the technical inspection guidelines. So for Shell Eco Marathon, to even put your race car on the track at the Indy 500, which is in Indianapolis for a North American competition, you have to pass 11 steps of technical inspection, and if you fail any one of them, you're out of the competition. So this ranges from brake checks, where we have to have our vehicle completely stop at a 20-degree angle. This goes like literally weight constraints from our driver to even dimension constraints, even whether or not our hydrogen fuel cell system actually works. But what really makes this interesting is interdisciplinary nature from when me and Ben were looking at the rules a little bit more in depth. And this is the case of me coming from a more sustainability background and looking at engineering from a sustainability aspect, and Ben then coming from more civil engineering, structural, mechanical engineering perspective, looking for ways for us in the beginning of the project to like, how do we kind of come together from these two different worlds, me not knowing as much about the mechanical systems, him not knowing too much how fuel cell works, and merging our two worlds together. This was the perfect project. Every single aspect of these regulations and every single aspect of the inspection guidelines require us to either learn something new from one another, learn something that we've never touched on, or even just work in the machine shop and try to figure out like, how do we construct something that we've never seen before.
All right, so just to give you guys some more background, again, the current vehicle that we started working on this year was started in 2012 as an E90 project. From there, it was a very old roll set. And over time, this entire competition has kind of changed. There's been added suspension, added safety systems that have been necessary to be part of it. There's a racing team in 2015 again, and then in 2018 there was another E90 done on it whenever they started to change the suspension rules, where they added a front suspension along with changing some of the safety systems. So this entire vehicle was sitting all during COVID, obviously because no one was here to kind of carry that forward. So it was kind of up to us to kind of pick up some of the pieces and get it running again along with Hana. And again, some of the current issues, we had a very outdated chassis model. So the issue with the current chassis was that it's a square aluminum. It was kind of what was sitting around, what was available. It's a very heavy material relative to what we actually need to support about a 100-pound driver. All of the brakes had to be updated to be hydraulic. Currently they were cable brakes, so that was no longer in the competition spec. Everything on our vehicle has to be hydraulic. There's an outdated steering in the front. There's a new rear suspension requirement as well as the front suspension. There's plenty of driver safety systems that need to be implemented on this vehicle. Then there's also the issue of the fuel cell not working after sitting for 2 years. So what we have highlighted here is what we decided to focus on for our E90 and try to get up and running to some sort of state by that part.
So you're gonna notice on your screen right now 2 very different pictures. Yours on the top, that's the current vehicle that we were working on when we first started this project. And to the bottom, that's what the vehicle should look like in competition. 2018, 2024 are very different. The winning vehicle in the Euro competition actually pretty much looks like a raised airfoil at this point. And we have a trike vehicle that barely raises above maybe like 6 inches from the bottom of the ground. Not actually acting like an airfoil either. And so, including all the rules, including all the updates that we had to put into consideration, and the fact that the competition is actually April of every single year, we decided really early on that we probably would likely not be able to compete in the 2024 April competition, and instead pivoted our goals towards creating a foundation, creating groundwork, and ultimately creating a playbook for future students to work on a 2025-2026 competition-ready vehicle. So what does that mean for us? Where do we even start? We went back to the drawing board. Shell Week Marathon, for the context of our vehicle, is really focused on fuel efficiency. How can we reduce the amount of hydrogen used for all 4 laps around an Indianapolis 500 that we need to be able to complete? And the first hypothesis, as Ben had mentioned in a previous slide and talking through it, was weight. Weight reduction, there's so much opportunity in weight reduction in the current vehicle, either redesign a new front suspension system, reducing the front suspension system weight, changing out all the material for the tubing and members from square aluminum tubes to maybe round tubing, or even just making the fuel cell area a little bit more compact and using less space in the chassis design. And to even just like help us understand a little bit more how weight affects the overall vehicle fuel efficiency, we then ran a couple of simulation models to kind of give ourselves an idea, like if we replaced a lot of materials on the vehicle, if we changed the weight, how much miles per gallon equivalent, how much fuel efficiency can we gain? And we were astounded, and it gave us a lot more confidence the fact that we got almost 2 to 3 miles per gallon equivalent gain for every single pound on the current vehicle that we can reduce. That's astounding. Current vehicles are around like maybe 50 miles per gallon, like max for a hybrid vehicle. And if we can reduce each part of our chassis by even like a couple pounds, we're getting a lot of mileage. And so, really just quickly walking through this next step of just verification for our fuel cell efficiency model. You're looking on your screen a waterfall graph that kind of dictates how we were looking at design implementations. So on the y-axis, miles per gallon equivalent increase, and on your x-axis, different design implementations, 1, 2, and synergies that are gained when you combine those implementations together. Our biggest one, number 1, chassis weight reduction by 33%. Our second one, frontal area reduction by 25%. That's essentially just to reduce the amount of drag experienced by the vehicle. And then third, thermal efficiency increases, which are either adding a cooling unit to the hydrogen fuel cell to make sure that it's not running too hot, or to always have a heating unit in the beginning of a race to make sure that the vehicle is not starting cold. A little counterintuitive actually, but what's really good to notice is that number 1, chassis weight reduction, that's the biggest jump. And what's even greater to actually notice is that when you put this weight reduction compounded with other design implementations, either like the frontal area reduction or thermal efficiency, it has multiplicative effects. For even like when we're putting a chassis reduction and front area reduction together, we're basically doubling the amount of mileage we're expected to get from just frontal area reduction. And even we're getting a third of the total a third of the thermal efficiency gains just from putting weight reduction with it together. And so that really gave us a lot of confidence that, okay, this is the big thing. This is what we're going to be working on for the rest of the semester, and we need to get that fuel cell simulation model, which is one last kind of push to make sure that we go in the right direction before buying a bunch of these materials. And so what you're seeing in your graph is on the left a total weight, like our total chassis weight versus different materials, and we replace every single member on that chassis. And so we're comparing chromoly, round chromoly tubing, aluminum round aluminum tubing, wrapped carbon fiber tubing, stainless steel tubing with the current square aluminum tubing. And you can easily notice on that left graph that wrapped carbon fiber is really great. It's really lightweight, and even then replacing the weights on the entire chassis and finding that fuel efficiency increases, we're finding that wrapped carbon fiber basically doubles every single other material, and that kind of gave us a thought to ourselves like, should we try this carbon fiber thing out? No other team has tried carbon fiber out as a chassis material. Every single team in the 2024 competition uses an aluminum chassis still. So maybe this could be the edge for the 2025-2026 team.
So now it came down to how do we actually build a carbon fiber chassis. So our primary issue is the fact that we don't have the ability to mold a entire chassis out, or I guess a whole molecule out of carbon fiber in-house here. So we had to try to figure out a way to basically conjoin tubes out of carbon fiber in a coherent and high-strength manner. So we don't have the luxury of just welding everything together whenever we're using aluminum. Now we kind of have to figure out a way to actually join everything together. So to start, to kind of attack this, we decided to make a SAT model to try to simulate what forces we would actually need to resist whenever we actually have our chassis. And basically what we found was what we would expect. So if we put a 200-pound driver right where we would expect him to sit, we're seeing maximum moments of about 500 pounds and 600 pounds, basically at the points where the wheels are supporting the chassis. And then as far as the maximum forces in the individual members, we're seeing a maximum of about 100 pounds and in compression and tension. So kind of moving forward, that came down to how do we actually join these now? So we did a little bit of research. We came up with the idea of using two-part epoxy to try to glue these together. A lot of the current methods to actually joining aluminum tubes are using some sort of epoxy, some sort of glue to basically join them together whenever you're not just molding the entire shape. And then we also came across a research article saying that adding glass filler beads in the epoxy would actually help with bond gap control, help the overall performance of the epoxy. So we decided to add those in as well. And then we came down to two different methods of actually building the joint. One being aluminum, going on the inside of the carbon fiber, and then one being a 3D print wrapping around the outside. And then we basically did two different versions of testing. One on bending at the midspan, and then one on tension, so just pulling the two ends, trying to rip it out. And basically what we found, in short summary, we're gonna go through the results right after this, is that the aluminum was great in tension, compression, and bending, but it is a lot heavier. And then also the 3D prints were great in axial tension and compression, but as soon as we introduced any sort of bending in it, then we often saw print failure. So we were able to add fasteners, and that really got us a lot of performance out of these 3D prints, but at the expense of not being able to really have any large moments on those joints. All right, so this is kind of a look at what we did on the UTM. As you can see, I'm a very bad welder. So this is not what you would typically see in the stress strain graph. This front portion here is basically the welds that I kind of sloppily put together on the test tube, crushing. And then this final portion is actually what you would expect with the linear elastic region. So basically what we were testing was the strength of the epoxy and how does it actually bind to the carbon fiber and the material that we're putting on it. And overall what we found was, so if we had a simulated maximum force of 900 pounds, we had a design goal of 300 pounds to kind of give us a factor of safety of 3. Basically what we found was the overall strength of the member was strictly reliant on the epoxy, which is what we were expecting, and it also agreed with kind of the 3M data sheets that we have. So whenever we loaded it in with any of the carbon fiber rods with the aluminum inserts, we saw maximum performances of upwards of 500 pounds, which met our design goal, perfect. And then also, whenever we matched it with the hardware inside the 3D prints, we also met our design goal as well. So we kind of were able to figure out two good systems that work well, but are good at different things. And then whenever we did a 3-point bend test on the joint itself, what we found was with a maximum simulated moment of 600 pounds, our design goal was 1,800 pounds. We basically found that we far exceeded that whenever we were loading approximately 1,000 pounds on to the middle of the joint before the carbon fiber would break. And actually what we found was, in some cases, especially with smaller diameter aluminums, the wrapped carbon fiber was actually able to bend the aluminum before it would break, which is kind of bizarre given that whenever you use just two different versions of carbon fiber, we basically tested two different versions of carbon fiber. I should have mentioned this earlier. But two different versions of carbon fiber that we were considering were large protruded, which are basically long strands of carbon fiber that are all kind of joined together. And then wrapped carbon fiber, where it's a bunch of intersecting layers that are kind of set at different angles and then wrapped into a single tube. But what we basically found was a large wrapped carbon fiber was the ideal material for our testing, and the protruded was too easily cracked to be able to be useful.
Right, and I guess the next really big thing to understand is the cost effectiveness of both of these joint connector methods. And so what you did notice from the bending test and tension test is that aluminum inserts performed way better. Actually probably gives us a higher factor of safety if we were to build the entire chassis out of it. But there's two big considerations still, which is the cost per pound saved and also the potential mileage increase from using these connector methods. And so final thing that we kind of did to help us understand that kind of cost analysis of it was, is it still worth it to actually use those aluminum inserts the entire way through, or would it still be better to actually use the 3D print connectors the entire time? And to give you also more context on those 3D prints, we were really lucky to be able to use the Mark Forge at the Makerspace, which is able to print a mixture of a PLA fiberglass and carbon fiber print, which is why we actually felt really favorable towards the strength of those 3D colors. And what you're going to be able to notice on the screen, probably already looking at it, is that for the amount of pounds we can reduce on the entire chassis, versus for the 3D color, it's really enticing. You're basically doubling the entire cost of the vehicle if we're using aluminum inserts for every pound saved. And then not only that, those large wrap 3D colors more than quadruple the total amount of efficiency gains that we can see. And so what do? We have these two really great connector methods, and how do we kind of mix both of them to make sure that we are getting the best of both worlds? And that's really our big conclusion from those joint connector discussions. So what you're going to see on your screen is two divisions of the area on our chassis that we're going to be using each different joint connecting method. So in the highlighted in yellow, that's basically the backbone of the chassis, because we're expecting those members to actually take way more tensile force, way more compressive force during every single race when a driver sits on it. We wanted to actually use these machined hollow aluminum inserts. And you're going to notice, we've been talking about solid aluminum inserts basically for the entire project right now, but now we're using hollow inserts. Had some really great experiments actually with our E14 students, where we removed a big chunk of that center aluminum of each insert up to maybe 0.5 inch diameter. We were able to see up to upwards of 1,000 pounds of compressive force. It was able to take that to the ultimate failure. And so it gave us a lot of confidence that, okay, we can actually use the aluminum inserts and still reduce the possible weight of each of those inserts on those joints. Secondly, you're going to see on the bottom those blue highlighted members. We're going to be looking towards those color methods. And why? As Ben was talking about earlier, these blue highlighted members are actually not taking as much tensile force, as much compressive force when we're loading a driver onto it. And so it gives a lot of confidence in the fact that, okay, these are members we can actually really go full in on the weight reduction and still have a strong level of confidence on their structural integrity. It's just, we don't really need them to be super strong and still get best of both worlds. And what you're seeing on the very left of your screen is that red connector piece, because you're going to notice on our chassis, there's actually a lot of different angles to connect these inserts, and then also these color methods, like how we're supposed to be able to do those angles with these straight inserts. So what we're going to do is that on every single color, it's actually going to have a threaded bolt at the very end. And for every machined hollow insert, we're going to be loading that onto a plate to be able to then bolt on those 3D colors onto the machine inserts. You can delve a little bit more into other questions, but essentially that gives us the best of both worlds for those connector pieces. And finally, we're just going to walk through really quickly some of the other mechanical systems that we were to work on. And this is kind of the last couple months after finishing these tensile and compressive tests. So hopefully it's going to be able to be very interesting.
Yeah, so we had to design the back suspension. We wanted to make it flexible enough to be put on the current chassis for testing and then be able to transfer onto a future chassis. So basically trying to make sure that our work is transferable and is not kind of in waste. So this was my original CAD model. This is kind of what I thought that I wanted to do. I wanted to have like some sort of V, weld it all together, run a bolt through the middle, run the suspension through the middle. And I started to realize I wouldn't be able to get the bolt into it. And then I started to kind of do some modifications on the fly and did some sort of ladder design, but it actually ended up being a better design in that way. So now with our current design, we were actually able to fit multiple suspensions kind of side by side. So we decide that one spring's not enough and we have the flexibility to put 2 in the side bays there. And then you can kind of see in that final photo what it actually looks like on the current chassis. But yeah, with this it was kind of a lesson in welding and also just kind of machinability parts.
Right, and really quickly going through what hydraulic brake is. The rules require us to have hydraulic brakes on both the rear and front suspension and wheels, like going forward. It's required. And we were using mechanical rim brakes on the current vehicle for a very long time, which aren't technically safe because of their just like interaction with the moving wheel, and we don't want to go with that moving forward. And so hydraulic disc brakes are required going forward. And so big thing to notice is that when you buy a hydraulic disc brake, especially for the one we bought for a mountain bike, we're not building a mountain bike. So we had to actually machine, we have to 3D print a brake attachment piece on your very left, then install, and then remove all the rear mechanical rim brakes, and wire the new hydraulic hoses through the entire vehicle before attaching it onto the new brake calipers onto our rear suspension system. And although we don't have quantitative data that actually prove that right now that those hydraulic disc brakes are performing a lot better than those mechanical rim brakes, we do know that from just our qualitative racing tests and just models for now, they do respond a lot better. And so we can actually show you in the demo later on. But yeah, now some conclusions and future considerations. This is the playbook. We're able to actually, from a lot of research and a lot of our foundational work through these last couple semesters, we're able to get a lot of confidence in like what really needs to be done and how to prioritize different aspects of this project. First and foremost, this is not a project just 3 people should be working on. Me, Ben, Harno, there's a lot of different systems that we ourselves still don't know how to like work around, and people who are a lot more interested in either the mechanical aspects of building a suspension out, the steering aspects, the electrical aspects of getting the wiring and the hydrogen fuel cell together. Like that's all different projects students can work on, and that's what gives a lot of like confidence. Like, hey, we should build out a team, and this is something a lot of students have the potential to actually work on. Secondly, there are still a lot of aspects that we haven't even touched on, like the aerodynamic aspects of the competition, like building a full cowl to cover the vehicle. That's something we didn't even think about until like the very end. We were thinking about aerodynamic considerations, or even just like safety systems. That's a huge thing. Like if any safety system fails, you can't even race. And so moving forward, a lot of things that a lot of students can work on, but we're still really happy with our research and just our designs in general. And so lots of people to acknowledge, lots of people to really appreciate throughout this project. Professor Carl Everbach, who's been our advisor, really helping us through the entire thing. Hano, who's been keeping the project alive until we hopped on, really like keeping it going.
Thank you to Jay. Thank you for putting up with me for long hours and teaching me how to weld. That's been a great skill to be able to kind of learn and hone into. And then thank you to Cassie for helping order a lot of materials.
And for both of us, all our friends and families who like listen to us ramble on and on and on about this project. And it's really been a great experience just to be able to touch most aspects of a car and just learn how to use them. But otherwise, take any questions now. After this talk, during the break, we're actually going to have a vehicle demo. I think we're going to do it outside since it's really nice now. And you can see how it runs. If you you meet the specific weight and height requirements, you could potentially sit in the vehicle. Who knows? But I'm taking questions now. Yeah.
When you're talking about miles per gallon, are you talking about like gallon of hydrogen gas?
Yeah, so miles per gallon equivalent is the conversion of hydrogen. So we're actually using like cubic meters of hydrogen. That's the measured unit. But we convert that to unleaded gasoline essentially. So using like net caloric values, actually right here. We have like this is a few fishes that really quickly throw on this Excel. Like I basically converted unleaded gasoline to hydrogen, and then I converted all of the hydrogen that we needed for the race and to get our miles per gallon equivalent.
How much does the layout of the track influence the design of the vehicle? Like if you're just like going to get a big oval.
So I was not considering that until I was reading an article with an interview of the winning team, I think the last 2 years.
Yeah.
They have someone who is like a math major on the team that did like GIS work and then optimized basically the speeds that they needed to travel and like the trajectory paths that they needed to travel on the track to optimize their fuel efficiency. Now, how much that actually changes everything, I'm not entirely sure. I mean, we have the belief that the winner this year had a single run where it had just like wind behind it in the perfect conditions. So they had runs at I think 130 miles per gallon, and then all of a sudden their last run they jumped to 190. So it's really dependent. I'm not sure if it really matters.
Slide. Also, like the Indianapolis 500 is a track that just round and round. There's not really crazy turns or anything. You're pretty much doing a straightaway. You're just doing straightaways basically and just kind of like curving the vehicle. So maybe just the turning aspect is really the biggest thing you may have to do, but overall, the track itself really does not change in terms of complexity a lot.
Yeah.
Could you just go to slide 13? I think it's just that model.
Yep.
Maybe I missed it, but could you talk a little bit about the assumptions you made for connections and what loading looked like?
Yeah, so my connection points were a little bit faulty in the fact that I had them fixed for moment resistance as well. I wasn't sure how to necessarily deal with the suspension joint because given that we're going on the inside of the members itself, I kind of saw that as having moment resistance as well. And then, yeah, so basically all three wheel points were fixed in the X, Y, and then also in the moments as well. So kind of just seeing specifically if we were to fix those points in space and actually have it kind of tied in, how does that interact? And then as far as like the individual joints and how it kind of translates to our final model, because we kind of have those pins going through the covered fiber joints, that's kind of ensuring that we have just strictly axial loads while the inserts will kind of take a lot of that moment capacity, if that makes sense.
Yeah, can you say what the loading was on it?
Yeah, the loading was 200 pounds directly on the center of that X.
Okay.
Yeah.
Yeah, I'm just wondering, like, you're mentioning with the safety factors, if that could take, if it needs to take 100 pounds and you can take, like, are there regulations in the checklist for the factor of safety on these numbers?
There is no specific regulation of factors of safety. It is just that it is safe and that, yeah, that's pretty much it. That it will not harm the driver pretty much.
Like, yeah, a big portion of the technical inspections just basically have to be that your driver should be a minimum weight of like, what, 110 pounds?
Yeah.
And that you have all your emergency buttons and like emergency shut down buttons like ready. And then I think a lot of the vehicle dimension and vehicle weight constraints basically stop you from having the vehicle just straight up on the ground. So
Yeah.
those are really the main considerations.
Yeah, there are clearance restrictions, but also part of our consideration was the fact that people were going to be climbing in and out of this vehicle. So we kind of needed to magnify a lot of the safety factors to make sure that someone isn't just climbing onto it and then breaks a member, because that would be a very expensive mistake. Yeah.
For the other ones where they have like the whole cattle on top, how do people get in and out of them?
That's honestly a great question.
So from what we've been able to see, it's those cows are pretty much detachable, and they just screw them on once they're in. And also, like, to be fair, like very similarly to like how like Formula One, like these drivers like recline like this. Like they're basically laying all the way down, except like the top back is like slightly up so you can see. Or even in the European vehicle, I think he's seeing through his legs, essentially. Yeah, it's essentially just an airfoil at this point, where you just like lock the person in.
Is that safe?
Yeah. It used to be safe. This is a 2020. This is a 2020 vehicle. So I think they have changed. They have changed that in the regulations where we have to actually have the hinge.
Yeah, there's also roll bars too, but kind of another consideration for the new vehicle is the fact that we probably will not be able to have like someone who's 200 pounds climb into this thing. The new competition vehicle is intended to be strictly for the driver, and then we can kind of add some flexibility around the old vehicle if we want to play around with it. If that kind of makes sense. Yes?
What are typical speeds in the competition?
I'm honestly not sure. I'm guessing fairly slow. But a lot of our baseline testing was kind of seeing how far we could push the actual fuel cell and see how much energy it actually has.
From what we were able to like get from previous competitors as well, just documentation online, like a lot of vehicles choose to average around 13 miles per hour. Our vehicle can go upwards to 25 in its current state, but that seems like be the best speed to go around the track.
All right, well, thank you very much, you two.